Hello and welcome to Physics for Play. In this episode, we're going to begin looking at the damped harmonic oscillator, which is a harmonic oscillator that's undergoing not only the restoring force from the spring, but also some frictional forces that will sap energy out of it. Let's get started. Now, if you've been paying close attention, you may have noticed that our solution for the simple harmonic oscillator doesn't quite mimic reality. And you can see that if I show you this animation, which is a bit closer to reality. So again, I have my mass on a spring. I've displaced it by some amount, and I'm going to set it oscillating. And in this animation, which is a bit more realistic, you see the mass eventually slows down and stops and returns to its equilibrium position. If I were to plot that, you can see that the displacement starts at some amplitude and then it oscillates, but as it oscillates, that amplitude gets smaller and smaller and smaller, decaying to zero. So how can we reflect the fact that in the real world there is friction? Friction will sap energy out of a mechanical oscillator so that it can't continue oscillating forever. So today we're going to explore how to do that. So if we look at our equations from last time, you can see we started with the definition of acceleration, which says that acceleration is the second derivative of position with respect to time, which we can write as x double prime. We worked with Newton's second law, which says that if you add up all of the forces on an object, you get its mass times its acceleration. And we used Hooke's law, which says that the restoring force of an object displaced from an equilibrium is equal to minus some constant, in this case the springiness of, or the stiffness of a spring, I should say, minus that constant times the displacement. Now we're going to want to add a second force that represents the dissipative force, the dissipative forces, or what we like to call the damping forces that sap energy out of the system. And we're going to be considering Stokes' drag, which has a force law that is still linear, so we can still use all of our complex exponential tricks. We're going to say that the damping force is equal to minus a constant times the velocity, which can be written as minus a constant, minus that constant times x prime, where x prime is the velocity. Now, if you've taken any fluid mechanics classes, you might have heard of a thing called Reynolds number. This equation works at low Reynolds number. We'll talk a little bit about what it means to be at larger Reynolds number. But for right now, we're going to consider a low Reynolds number because it keeps our equations linear and it makes them easy to solve. So we are going to, actually let me keep my equations out here for a little while longer. We're going to rewrite the differential equation that we solved earlier, except this time we're going to include this damping force, which will account for the friction in the system. So what we're going to do, as we did in previous episodes, we're going to look at our differential equation. We are going to solve using the guess and check method. And actually, I'm going to skip this step and jump right to the solution. We'll leave that as a home exercise. And then in the next video, we'll show you how to solve it with dsolve. It's the same thing you would have used to solve before. It's just we need to update the differential equation. We'll also explore the physics in that video as well. But let's start with what that differential equation is going to look like. So we have the force equals the mass times the acceleration, where we can write the acceleration as x double prime as a function of time. And that's going to equal the sum of the forces, where the first force is given by Hooke's law, minus the spring constant times x. And the second force is given by that Stokes drag damping force equation, a constant times the velocity x prime of t. What I will do, I will show you the ansatz that you should guess. And again, I'm going to leave this as a home exercise. But if you guess the solution x of t, and then you use our complex exponential trick to make the guess that the solution is going to be some amplitude times e to the I times a constant p times the time plus some phase shift alpha, you can show that this is a solution. You'll have to make quite a few algebraic substitutions. But after you manipulate the algebra, what you'll find is that you can rewrite this e to the I pt plus alpha. You can rewrite that in terms of a real part and an imaginary part. And when you take just the real components, you are left with something that looks like this. So much like before, we have a cosine omega t plus alpha. But now we also have this exponential decay in here as well. And the exponential decay describes how the amplitude decreases over time. So it's e to the minus a new constant gamma times t is time, times t divided by 2. Now, I should note there are a few constant substitutions in here, one of which is you have omega naught, which is the square root of k over m. Now, that is the frequency, or rather the angular frequency, at which the spring would oscillate in the absence of any damping forces. We also have gamma, which is really just related to the damping force constant. It's equal to that damping force constant B divided by M. And then we also have this new angular frequency. And this is going to be the angular frequency that shows up when you do have damping in that motion. And you can see it's equal to the square root of omega naught squared minus gamma squared over 4. So you can see that when we have no damping, gamma goes to 0 because there is no damping force, which means omega equals square root of omega naught squared, which means it just equals omega naught. So with no damping, you just get back to the original angular frequency that you had for simple harmonic motion. Now, we are going to go ahead and we're going to plot, we're going to make a plot of what this looks like. So I am going to define some values here. Let's say I'm going to plug in just a little bit of damping force. I'll make that B equals 0.1. I'll make the mass equal to 1. And I am going to define, I'm going to just copy and paste this down here so I've got a fresh cell to work with. And I'm going to plot x of t. And we're going to plot that from t goes from 0 to 10. And let's see, what's blue here? I need to define an amplitude, and I need to define a phase shift. I'll set the phase shift equal to 0 for now. And I think, I need to define an omega. Actually, what I'm going to do, I am just going to take these definitions and plop them right here. So I've got my omega naughts, I've got my gamma, I've got my omega, and that should be, we're just going to run this and see if that works. Okay, so I've defined all my constants. Let's clean this up just a little bit. Let's label some axes. So we'll say the x-axis is time, t in seconds. We'll say that the y-axis is the displacement, x in meters. plot, we'll see that looks just fine. I'm gonna actually give a plot range of 10, and the reason why is that I want to wrap this in a manipulate function. So I want to be able to play around with this a little bit more dynamically. So I am going to wrap my plot and all of these other functions into a manipulate. And I want to be able to manipulate a few different variables here. So first, I am going to have an amplitude that goes from -10 to 10. I am, and actually let me start that with an amplitude of, let's say 10. We'll make it as big as we can, and I'll give it a name. So you can see with this, I can change the amplitude back and forth. That's easy enough. I can give it a negative amplitude if I want. But I don't want to manipulate just the amplitude. I also want to manipulate some other variables. Let's manipulate omega naught. Sometimes you hear this referred to as the natural frequency. And that let's see, that's going to get units of radians per, well, I'll leave the units off for here since I'm just putting it in a manipulate. We'll let that go from 0 to 10. And if I run that, now you can see, why are you, it's getting cranky at me because it's resetting omega naught. I actually do not want omega naught in here. So I'll put that on the outside. And you'll see, let's actually start omega naught a little smaller. We'll make it 1 to start. And you'll see we can increase and decrease the frequency, the angular frequency there, which is going to stretch and compress the graph. Let's see what happens if we change, the mass. Oops, it should be natural frequency, not natural. We'll let the mass, I don't want to let the mass go to 0 because you'll be dividing by 0 at a certain point. So we'll just make it get small. We'll make it 0.1. So for a small mass, you can see it does not have a lot of inertia, so it kind of damps out a lot quicker. For a larger mass, I can make it so that the damping is very small. And it continues its oscillatory motion without much of a change. Let's put in, oops, let's not forget a comment. Let's put in an angle, or a phase shift rather. I'll let my phase shift go from 0 to 2 pi. And you can see that just changes where the graph starts in phase. So nothing too surprising there. And we can also play around with the damping constant, B, which I'll call my damping coefficient. And we'll let that go from, we'll say 0 to 3. So if I decrease the amount of damping, if I make it 0, you can see it doesn't decay at all, or I could make it decay very, very quickly. So we can start to play around with the solution for our damped harmonic oscillator. Now, we can also animate this solution as well. I'm not going to go through the code in explicit detail other than to say I've copied it down from the example section, the example video that we did earlier. And I'll show the code here in case anybody wants to pause the video and run through the dynamics of it. But basically, we set up our function. We define what the particle will look like. It'll just be a sphere. We define what the spring will look like, and then we animate it by showing the spring and the particle. And if we do that, hit Shift and Enter, we get an animation that looks very similar to what we had before. Of course, we can start to explore the physics of this by changing some of the parameters. So if I reduce the amount of damping, you can see for the most part it does not decay very much. If I massively increase the damping, you can see that it decays very quickly and goes basically right to its equilibrium point. That is all we will do for today. So next time, we will show you how to come up with the solutions in Mathematica using the dsolve command. So you don't even have to make your ansatz and go through the algebra to check it. We can just go and jump to the solution directly. Like the video if you liked it, and if you'd like to see more, please click subscribe.